Using multiple smaller contactors in place of one larger contactor for motor control is permissible, provided the specific conditions are met. The National Electrical Code, Section 430, and NFPA79, Sections 9 and 10, mandate an emergency stop button for machinery incorporating motors. Conventionally, the emergency stop mechanism functions by opening a contactor, thereby cutting off power to the motors. Motor groups performing a shared function should have a single disconnecting mechanism. Consider a scenario involving 4 25 amps motors within a system. The economic viability of using 260 amps contactors each connected to 2 motors is compared to employing a single 120 amps contactor serving all 4 motors. A single stop button configuration can energize both 60 amps contactor coils in parallel. This setup is compliant with regulations if the load on each contactor, multiplied by 115%, remains within its rated capacity. Avoid connecting 260 amps contactors in parallel and connecting all 4 motors to both contactors. The critical factor is ensuring that each contactor's load, when increased by 15%, does not surpass its rating. The 115% rule is a safety margin implemented to prevent contactor overheating and potential failure. This rule dictates that the continuous current load on a contactor should not exceed 115% of its specified rating. For example, with a 60 amps contactor, the continuous current load should not exceed 69 amps, which is 60 amps times 1.15. If you have 2 25 amps motors connected to a 60 amps contactor, the total current draw would be 50 amps. Multiplying 50 amps by 1.15 yields 57.5 amps, which is still below the 60 amps rating of the contactor. Firstly, calculate the total current draw of the motors connected to each contactor. Secondly, multiply the total current by 1.15 to determine the adjusted current. Thirdly, compare the adjusted current to the contactor's amperage rating. If the adjusted current is less than or equal to the contactor's rating, the setup is acceptable. If the adjusted current exceeds the contactor's rating, a larger contactor must be used. To illustrate further, consider a situation with 3 20 amps motors and 1 10 amps motor, totaling 70 amps. If the contactor is rated at 70 amps, multiplying 70 amps by 1.15 results in 80.5 amps, exceeding the contactor's rating. In this case, a contactor with a higher rating, such as 85 amps or 90 amps, should be used to comply with the 115% rule. The 115% rule accounts for fluctuations in voltage and current, temperature variations, and the inherent characteristics of the load. It is a precautionary measure to prolong the lifespan of the contactor and prevent premature failures. In addition to the 115% rule, other factors must be considered when selecting contactors. These include the voltage rating, the horsepower rating, the inrush current rating, and the type of load. The voltage rating of the contactor must be equal to or greater than the voltage of the circuit it will be controlling. The horsepower rating of the contactor must be equal to or greater than the horsepower of the motor it will be controlling. The inrush current rating of the contactor must be equal to or greater than the inrush current of the motor it will be controlling. The type of load will also affect the selection of the contactor. For example, a contactor used to control a resistive load will not need to be as large as a contactor used to control an inductive load. To delve deeper into contactor selection, it is essential to understand the different types of contactors available. Definite purpose contactors are designed for specific applications such as HVAC systems or lighting control. They are typically less expensive than general purpose contactors, but they may not be suitable for all applications. General purpose contactors are designed for a wide range of applications. They are typically more expensive than definite purpose contactors, but they offer greater flexibility. Solid-state contactors use semiconductors to switch the load. They offer several advantages over electromechanical contactors, including faster switching speeds, longer life, and reduced noise. However, they are typically more expensive than electromechanical contactors. When selecting a contactor, it is important to consider the ambient temperature in which it will be operating. Contactors are typically rated for operation in ambient temperatures up to 40 degrees Celsius. If the contactor will be operating in a higher ambient temperature, it may be necessary to derate its amperage rating. This means reducing the amount of current that the contactor is allowed to carry. Contactor derating is typically specified by the manufacturer in the contactor's datasheet. It is important to follow the manufacturer's derating instructions to ensure that the contactor does not overheat and fail. In addition to derating, it may be necessary to provide additional cooling for the contactor. This can be done by using a fan or by mounting the contactor in a well-ventilated enclosure. In summary, when selecting contactors, consider the following factors: voltage rating, horsepower rating, inrush current rating, type of load, ambient temperature, derating requirements, and cooling requirements. Proper contactor selection is crucial for ensuring the safety and reliability of electrical systems. Connecting two 60 amps contactors in parallel to power all four motors is not recommended. This practice can lead to unequal current sharing between the contactors, potentially overloading one contactor while the other remains underutilized. Such an imbalance can create a hazardous situation and increase the risk of a fire. Unequal current sharing can arise due to slight variations in the contactor's internal resistance or impedance. Even minor differences can cause one contactor to carry a disproportionate share of the total current. When a contactor is overloaded, it generates excessive heat, which can damage the contactor's internal components and insulation. This can eventually lead to a short circuit or ground fault, resulting in a fire. The NEC and NFPA79 provide guidelines for the proper installation and wiring of contactors. These guidelines are designed to prevent electrical hazards and ensure the safe operation of electrical equipment. It is essential to follow these guidelines carefully when installing contactors. In addition to the safety concerns, connecting contactors in parallel can also reduce the lifespan of the contactors. The overloaded contactor will experience increased wear and tear, which can lead to premature failure. It is generally more cost-effective to use a single contactor that is properly sized for the load than to use multiple smaller contactors in parallel. A single larger contactor will typically be more reliable and will have a longer lifespan. The proposed scheme of using two 25 amps loads on each 60 amps contactor with all contactor coils connected to a single stop button is acceptable as long as each contactor's load, when multiplied by 115%, does not exceed its rating. This setup meets the requirements of the NEC and NFPA79. The emergency stop button must be readily accessible and clearly labeled. It should be located in a position where it can be easily activated in the event of an emergency. The emergency stop button should be red in color and should have a yellow background. The emergency stop button should be wired to a normally closed contactor that will open when the button is pressed. This will interrupt the power supply to the motors and stop them from running. The emergency stop circuit should be designed to be fail-safe. This means that if any component in the circuit fails, the motors will stop running. For example, if the emergency stop button is damaged or the wiring is cut, the motors will stop running. The emergency stop circuit should be tested regularly to ensure that it is functioning properly. The test should be performed by a qualified electrician. The emergency stop circuit should be documented in the machine's electrical schematics. The electrical schematics should be readily available to maintenance personnel. It is important to train all personnel who operate the machine on the proper use of the emergency stop button. Personnel should be trained to recognize emergency situations and to activate the emergency stop button immediately. Personnel should also be trained on the procedures for restarting the machine after an emergency stop. In addition to the emergency stop button, the machine should also have a disconnecting means. The disconnecting means is a device that can be used to completely isolate the machine from the power supply. The disconnecting means should be readily accessible and clearly labeled. It should be located in a position where it can be easily activated in the event of an emergency. The disconnecting means should be a switch or a circuit breaker. The disconnecting means should be rated for the voltage and current of the circuit it will be disconnecting. The disconnecting means should be wired to disconnect all ungrounded conductors of the circuit. The disconnecting means should be capable of being locked in the open position. This will prevent the machine from being accidentally started while it is being serviced. The disconnecting means should be tested regularly to ensure that it is functioning properly. The test should be performed by a qualified electrician. The disconnecting means should be documented in the machine's electrical schematics. The electrical schematics should be readily available to maintenance personnel. It is important to train all personnel who operate the machine on the proper use of the disconnecting means. Personnel should be trained to recognize emergency situations and to activate the disconnecting means immediately. Personnel should also be trained on the procedures for restarting the machine after the disconnecting means has been activated. Proper contactor selection, emergency stop implementation, and disconnecting means are essential for ensuring the safety of personnel and equipment. Adhering to the NEC and NFPA79 guidelines is crucial for compliance and safety. Consider also the short circuit current rating (SCCR) of the contactor. The SCCR is the maximum short circuit current that the contactor can safely withstand without failing. The SCCR of the contactor must be equal to or greater than the available short circuit current at the point of installation. The available short circuit current is the maximum current that can flow in a circuit under short circuit conditions. The available short circuit current can be determined by performing a short circuit study. A short circuit study is a detailed analysis of the electrical system that calculates the available short circuit current at various points in the system. The short circuit study should be performed by a qualified electrical engineer. The SCCR of the contactor is typically marked on the contactor's nameplate. The SCCR is typically expressed in amps. If the SCCR of the contactor is less than the available short circuit current, a current limiting device must be installed upstream of the contactor. A current limiting device is a device that limits the amount of current that can flow in a circuit under short circuit conditions. Current limiting devices include fuses and circuit breakers. The current limiting device must be sized to protect the contactor from the available short circuit current. In addition to the SCCR, it is also important to consider the withstand rating of the contactor. The withstand rating is the maximum voltage that the contactor can safely withstand without failing. The withstand rating of the contactor must be equal to or greater than the maximum voltage that can occur in the circuit. The withstand rating of the contactor is typically marked on the contactor's nameplate. The withstand rating is typically expressed in volts. If the withstand rating of the contactor is less than the maximum voltage that can occur in the circuit, a voltage limiting device must be installed upstream of the contactor. A voltage limiting device is a device that limits the amount of voltage that can occur in a circuit. Voltage limiting devices include surge suppressors and transient voltage suppressors. The voltage limiting device must be sized to protect the contactor from the maximum voltage that can occur in the circuit. The 115% rule applies to the continuous current rating of the contactor, not the inrush current. Motors typically draw a much higher current when they are first started than they do when they are running at full speed. This is known as the inrush current. The inrush current can be several times the continuous current rating of the motor. The contactor must be able to withstand the inrush current of the motor without failing. The inrush current rating of the contactor is typically marked on the contactor's nameplate. The inrush current rating is typically expressed in amps. When selecting a contactor for a motor application, it is important to consider both the continuous current rating and the inrush current rating. The contactor must be sized to handle both the continuous current and the inrush current of the motor. The NEC provides guidelines for selecting contactors for motor applications. These guidelines are found in Article 430 of the NEC. Article 430 provides information on the minimum size of the contactor, the overload protection requirements, and the short circuit protection requirements. It is important to consult Article 430 of the NEC when selecting contactors for motor applications. In addition to the NEC, NFPA79 also provides guidelines for selecting contactors for industrial machinery. NFPA79 is a standard that covers the electrical design, installation, and maintenance of industrial machinery. NFPA79 provides information on the minimum size of the contactor, the overload protection requirements, and the short circuit protection requirements. It is important to consult NFPA79 when selecting contactors for industrial machinery. The use of multiple smaller contactors instead of one larger contactor can be a cost-effective solution in some cases. However, it is important to carefully consider all of the factors discussed above before making a decision. It is also important to consult with a qualified electrical engineer to ensure that the installation is safe and compliant with all applicable codes and standards. In conclusion, while utilizing multiple smaller contactors instead of a single larger one is permissible under specific conditions outlined by the NEC and NFPA79, it's crucial to adhere to the 115% rule, avoid parallel connections that could lead to unequal current sharing and potential hazards, and carefully consider factors such as voltage and horsepower ratings, inrush current, ambient temperature, and short-circuit current rating. Always prioritize safety, code compliance, and consulting with qualified professionals to ensure a reliable and secure electrical system.